Hello and welcome to this short introductory video series about machine learning. My name is Bojan and the main goal of my work is to empower more people to take advantage of machine learning by making it more easy to use. In this video series, we try to cover the most important concepts and show how they fit together without going too much into details. If you're a beginner trying to make sense of the field of machine learning, we believe these videos could help you get started. Here's an outline of the topics we'll cover in this video series. Each topic is formulated as one particular question related to the field. In this video, we will focus on question number 5. As a quick recap of the previous video, we went over various types of machine learning models, and we also tried to define what a machine learning model is. The simplest way to look at a machine learning model, especially as a user, is to look at it from the outside as a black box and see how we interact with it. Namely, a model is something we can train by using training data. The result of this process is a trained model, also called a predictor, which can take new, unseen data and make predictions that we use as solutions to our specific problem. The question becomes, how do we go about training this model? Is there some process to it? That is precisely the topic of this video. Here we ask, what is the workflow of someone who practices machine learning that takes them from a problem to a solution? We divide the workflow into 5 steps. Of course, what we present here is a rough separation, as these steps are not strictly defined. However, in our experience, this is a relatively useful guideline on what usually takes place when solving problems with machine learning. The first step is, of course, defining the problem and acquiring the data we need. As we've seen, data is essential to learning, and the quality of data will usually determine the final performance we will be able to observe. Data usually comes in some raw form, which unfortunately cannot immediately be passed into our models. Because of this, we usually need to have a pre-processing step, which usually involves a process called feature engineering. Features are like variables that contain information about our data points, and engineering features is the process of expanding the array of variables we have at our disposal, which can usually help the model perform better. Then, we need to select one or more models we would try to apply to our problem. If we only have one model available, then this is not a big issue. However, we usually are able to substantially improve our chances of a good solution if we expand our search over a larger pool of potential models we could use. Each model we decide on, we of course need to train. Models usually come with some parameters which cannot be learned, called hyperparameters. Discovering good values of these hyperparameters is called tuning the model. Finally, once we have a trained model, we want to measure its performance in order to evaluate its quality. Then, if the model is good enough for what we need, we are done. However, if we are not satisfied with the performance, we need to go back to some of the previous steps and repeat until we are finally satisfied. In the remainder of this video, we will expand a bit on each one of these steps to see what goes into them. Finally, we will consider 2 more related concepts that are not steps but are still worth noting, and they are overfitting and cross-validation. So, let's jump into the first step, defining the problem and acquiring data. The first step to define the problem is to identify what kind of input and output data we have. For example, if the input data is an audio recording of a person speaking, and the output is a transcript of the sentence being spoken, then we are dealing with a speech recognition problem. Another important aspect of a problem definition is the choice of the objective. Namely, an objective lets us compare different solutions and should express whatever it is we care about the most when evaluating any solution. Example objectives for speech recognition include percentage of correctly identified words, which is a relatively simple measure that just counts how many words we got right without caring about ordering. However, in speech recognition, we usually also care about outputting a correct sentence. Therefore, we would probably prefer a measure which pays attention to the order of words. One example is the measure called edit distance. Finally, once we have defined our problem, we need to make sure to acquire data, and preferably lots of it. For this example problem, the data acquisition would likely involve recording different people while they are pronouncing some sentences, and then transcribing those sentences so that we also keep the textual form, which will serve as a supervision signal. Once we've defined our problem and we've acquired our data, we're probably going to need to do some pre-processing before we can move on to the subsequent steps. As a quick example of a common form of pre-processing, we point out one-hot encoding. For example, if our dataset is stored in a table and some column of that table represents different pets a person can have. The problem is that machine learning models are essentially mathematical structures that often expect only numerical data, which means they cannot process words directly. Therefore, one way to encode these categorical values into a numerical format is to replace the pet column with, for example, 4 columns, in case we have 4 different possible categories. And then each column will have either a value 0 or 1, depending on the value of the input row. For example, if a person has a pet cat, then we will put a 1 in the cat column and 0 elsewhere, and so on. The general issue is that data is very heterogeneous, and as we've said, models can usually work only with numerical data. Furthermore, it is usually beneficial if this data is well behaving in some usually mathematical sense. Specifically, if the average value of all the rows in a specific column is 0, the model can deal with that column much more easily as it is more numerically stable and hence easier to compute. Finally, sometimes it is beneficial to completely transform the representation of the data. For example, if a column with words doesn't contain only 4 values, but instead it has values taken from a large dictionary from, say, 10,000 words, it is not practical to have 10,000 columns. In that case, we can employ a technique called embedding, where a word is embedded into a multi-dimensional space that may not have 10,000 dimensions, but merely 100. Furthermore, a good word embedding would also usually embody some semantical structure of our dictionary. It is common that similar words end up close to each other when projected into the embedding space, as we can see here. Sometimes our data requires us to apply even more intelligent techniques to enable it to better represent the information we want the model to focus on. These techniques usually involve producing some novel data representations through a process we call feature engineering, while at the same time removing some unnecessary features, which we call feature selection. It is often the case that to perform these tasks successfully, one needs some deeper understanding of the nature of data we are dealing with. We refer to this understanding as domain-specific knowledge. The end goal of feature engineering is to produce features that are able to reveal to the model the most useful information, while hiding, if possible, any information that might confuse the model. We give 2 examples of non-trivial features that require a deeper understanding of the data which computers simply don't have. One is the representation of time. The challenge is that the difference between, let's say, 10:15 and 10:16 is 1 minute, which is the same difference between 10:59 and 11 o'clock. However, the numbers 59 and 0 are quite far apart. This is trivial to us humans who know how to read time, but poses a hard encoding problem to a machine learning model because it is hard for us to reason about the circular nature of our time formats. A much better representation might be one where we express time in terms of angles of clock hands. That way, we explicitly encode the similarity between all time points that are 1 minute apart. Another example is the representation of chemical compounds. A trivial approach might be to encode them as letters and numbers in some chemical notation. However, that notation is not even trivial for most humans, let alone for a machine. Therefore, a much better approach might be to encode some domain knowledge and represent atoms or atom groups as vectors, which we can compress into a single vector representation that might be better at encoding the important information about a molecule. This is usually quite a difficult task for a practitioner and usually requires a lot of time and effort to get it right. Moving on to the third step, we have the challenge of selecting applicable models. As we mentioned, it is often the case where multiple models are viable candidates for our problem, but they might differ in the performance they are able to give us. We may have to choose between decision trees, support vector machines, or neural networks for our classification problem. It is possible that the choice is not trivial and that we might need to consult the latest research to see if it can give us some good approaches and methods. In the best case, we could apply some ready model that someone already implemented. On the other hand, we might have some highly specialized model that is promised to work very well, but we don't have a ready implementation, so we might need to write the code for it ourselves. In either case, it is good to be aware of several very popular software frameworks in case we want to apply an existing model or implement one from scratch. We have scikit-learn, which is one of the most popular frameworks written in Python that is mostly used for what we call classical machine learning models. This basically means all models that are not deep neural networks. Then we have TensorFlow with its subcomponent Keras. Then on the other side, we have PyTorch and Caffe, all of which focus primarily on deep learning models. Finally, we have an example of a framework that is built using the C# language, which is similar to scikit-learn, called ML.NET. Moving on, each model we have, we will need to train and tune. The inputs to this step is the training data and a set of hyperparameter values, for example, the number of layers in a neural network. These are fed into a model that then, as a result of the training process, produces a trained model. The key thing to training a model is having good training data. Depending on the way they are implemented, some models can take advantage of special hardware, for example graphics cards, which enable much more efficient training. And, as mentioned, most models have hyperparameters, which have to be set before training because they are not learnable. The best approach we know of for finding the best value for most hyperparameters is, unfortunately, to simply try and see how well the model performs with different settings until we find a good setting. The final step we want to describe here is measuring the quality of a model. Since we've seen that a machine learning workflow is a complex process that involves potentially many iterations with many trained models, it is crucial to evaluate those models somehow in order to pick the one we want to use as our final solution. We start from a dataset, which typically influences the potential choice of an objective. We use data in combination with the model to compute some estimated quality score. Here are some examples of objective functions which we can name depending on the type of problem. For classification, we have accuracy, precision, recall, the F1 score, AUC or area under curve, and so on. For regression, we have mean squared error, mean absolute error, root mean squared error, the R2 score, and so on. At different stages of our workflow, we might have to perform quality measurements using different types of datasets. These types of datasets include the training dataset, the validation dataset, and the test dataset. The primary usage of the training dataset is to train the model. A score computed over this dataset is usually a measure of how well the model fits the data. If this score is bad, then we might be experiencing issues with training itself. The primary usage of the validation dataset is for selecting models and for tuning them. The model hasn't seen this dataset during training, so it is the first dataset we might use to measure how good a trained model is at generalizing to data it hasn't seen before. The final type of dataset we typically have is the test dataset, with its primary usage being the final score estimate. The reason it is separated from the validation dataset is that the validation dataset is used by us during the process of tuning the model, so it was used to influence our choices in a way. In order to have a relatively reliable final estimate of a score, it is best to do it with a dataset that we never used before. In a typical machine learning workflow, these datasets have different sizes and are usually taken as distinct portions of some common data pool. The training dataset is usually the largest, with the validation and test being relatively small but still substantial enough to be able to give good estimates. Now that we've covered the steps of a machine learning workflow, we would like to go over two concepts that are very relevant to measuring the quality of models. The first one is cross-validation. The problem that often occurs is that we might not have enough training data to partition it into separate training and validation sets. To maximize the utilization of these smaller datasets, we can have multiple training and validation iterations over the same dataset. The way we would normally go about it is to start from our original training data and split it into some specific number of subsets, called folds. Let's say in this example we have 4 folds. Then we will have 4 iterations, and in each iteration we would use one of the folds for validation and the rest for training. In each iteration, we take the trained model and compute the validation score based on the split of that iteration. Finally, we average over all validation scores to compute a final score, which we call the cross-validation score. This score is similar in nature to the validation score and is used for the same purpose. The only difference is that it was obtained through this iterative cross-validation procedure. One more important concept that we would like to cover in the end is the concept of overfitting, along with its corresponding opposite concept called underfitting. Let's say, for example, we train one of those linear models on some simple data. Depending on the choice of hyperparameters, for example, the strength of regularization we want to apply, we may have different outcomes. It is important to note that the final goal of machine learning is not to simply fit the training data, but to capture the right pattern from that data which will enable it to make good predictions on new data it has never seen before. Hence, we might have 2 scenarios which are both undesirable. Our model might lack the flexibility to follow the curve of our data distribution. We call this scenario underfitting. In other words, we say that our model has high bias. On the other hand, if our model has too much flexibility, it might try to follow every single data point. This is a problem, as the reason our data points are slightly scattered is due to some noise in our measurements. However, this noise doesn't represent the data distribution. It is just an artifact of our faulty measurements. Hence, we would prefer that our model can ignore these bad artifacts. If it cannot, then we say the model has high variance. The potential causes of underfitting include models that are too simple or too constrained, or there might be some problem with optimization. Some common potential causes of overfitting might be a model that is too complex, or a dataset that is too small. If you remember what we've said about the connection between model complexity and the amount of data needed, you can see that these 2 causes are actually related with each other. One way to notice if a model is overfitting or underfitting is to look at how the training and validation score, or error, which is its opposite, behave as we make more iterations in our training and tuning process. If both the training and validation errors are high, which usually happens in the beginning when we don't have a good model yet, then we are in the underfitting regime. If the training error is low, but validation error is high, which usually happens when the model is quote-unquote overtrained, then we are clearly in the overfitting regime. The perfect middle ground is achieved when the training error is relatively low and the validation error is at an optimal point. Then, neither more nor less training will improve the validation score, which is likely the best we can achieve from the current model. That's all we have for this video. We hope it managed to clarify some basic concepts. Make sure to check out our next video, where we will see how the machine learning workflow that we just talked about can be made simpler and easier to use through automation. Finally, feel free to check out our website and learn about our very own effort to make it easier to use machine learning for your specific problems. You'll find all the links in the description.